the introduction. Thank you so much for the invitation. Uh, so today I'm going to be talking about results from a couple of papers that I put out the past year. Both had to do with global existence from the 3D Muskat problem. The first, which I put out near the beginning of last year, was about a 40-page paper where I tried to be very general and there and put into that paper as much of what I knew how to do at the time as I could, in as great generality as I could. Uh, and then the second paper was a 10-page paper I put out a few months later, where I tried to make the proof as simple and short as possible, so that hopefully somebody would read it. So I'm going to be talking to you about all those results today. Now, to start off, I should actually say what the Muscat problem is. So it was first derived by a geologist, Muskat, in the 1930s. He was trying to describe the encroachment of water into tar sand. So really the issue is to describe the evolution of the interface between two immiscible, incompressible fluids in a porous media. So oil and water and sand. Mathematically, what this turns out to be is the incompressible porous media equation, which is this system, where first we have a conservation of mass. Our fluid velocity is given by Darcy's law, which says basically that in porous media, the velocity is proportional to the net force acting at the point. We have divergence U equals 0 for incompressibility. And then we're dealing with immiscible fluids, and the specific concept we want to look at is the case where our density is given by the sum of two indicator functions. Rho 1 for fluid 1 and rho 2 for fluid 2. I'll be dealing with the case where the viscosities of the two fluids are the same, and so only focusing on the density jump case. Now, where I'll be working is in the so-called stable regime, which is where this fluid domain d of t is a supergraph. So the boundary of d is the graph of some function, and we want the lighter fluid above the heavier fluid, so that things are physically stable. And so we just have simple schematic, two regions for two different fluids, separated by the graph of some function. And what we want to do is describe how these regions change over time, which corresponds to how does this function f change over time. Because in fact, the system, you can, if you through it, it simplifies to just an equation for this function f, which we can write in a couple different ways. This first written like equation 2, but after doing some integration by parts and change of variables, the way I'll be working with it is always in this form for equation 3. Let's see. Now, if we are considering around a flat interface, then this problem just linearizes to the fractional heat equation. And so that tells us that for at least small data, this is really a parabolic problem. It should be regularizing. Or more explicitly and more generally, if we look at this kernel here, which this kernel really has to do with the distance in 3 space between 2 points on this graph. That's what that is. Then it's always bounded from above by the kernel for the half Laplacian. And as long as you're Lipschitz, it's bounded from below. And so what that tells us is that you would expect generally from elliptic regularity theory that as long as our Lipschitz norm remains uniformly bounded, then our function f solves a uniformly parabolic equation. Should be regularizing. We should get global regularity. That's what you expect. Now, so what is known? We have a lot of results on local well postness. The equation, the form I wrote down, was first shown to be locally well post by Cordova and Concedo in 2007. It shows locally well post in HK for K greater or equal to 4. The key fact is they needed K to be large enough so that the interface was C2 alpha. Since then, there's been a lot of chipping away at the regularity requirements on your initial data for local well postness, which got into any, so you can get about any subcritical space into the R3D. And recently in a series of papers, for the 2D case, they've actually gone all the way down to H3 halves, which is the scaling invariant space. Now Zarden win in a series of 3 papers to this. It was some very impressive work. So that is where local well postness stands. Let's see, we also always have a couple of maximum principles. The interface is always bounded in L infinity. So we have L infinity maximum principle. And you also have an L2 maximum principle. But this L2 energy estimate, unlike a lot of L2 energy estimates for elliptic equations, you don't get a gain of a derivative. They just show that the L2 norm is decreasing in time. Now, and so what makes this problem interesting is that despite being such a relatively simple nonlinear version of a parabolic equation, just a nonlinear perturbation of the fractional heat equation, we still actually do get blowup. So the first kind of blowup that is shown to occur is wave turning, which is not a blowup of the surface or of the boundary of the interface between the 2 fluids, but of our parametrization. The graph of the function f blows up in finite time, after which point you have a wave, turns over. The name really tells you everything. No. And so you might argue that that really shouldn't be counted as a valid kind of blowup because it's a blowup of our parameterizations, not a blowup of the actual physical object. But it's been shown that actually after a wave turning curve, we have an example where there's blowup in C4. So we actually do have regularity breakdown as possible. And more generally, the behavior of the interface just becomes a lot more complicated once wave turning occurs, because you can have a solution where a wave forms, turns over, but then everything flattens back out after some finite time before it turns over again. And so the behavior of the problem is just much harder to deal with. Let's see, so in summation, what we have is a parabolic problem that is locally well posed with some low regularity maximum principles, but finite blowup does happen. And once wave turning occurs, the whole system becomes much more difficult to deal with. And so that naturally raises the question of, well, how can you prevent wave turning? When do you have a global solution, and what kind of assumptions can you make to get based on your initial data in order to guarantee that? Now, the Muskat problem has a natural rescaling. And so you would guess that the right kinds of assumptions to make are upper bounds on some scale invariant quantity. In particular, I'll always be working with all my results are basically about the Lipschitz norm, which is scaling invariant. Now, for global existence, I'm going to split things up between the 2D and the 3D cases because much more has been done in 2D case. So if you have smooth initial data and this Fourier norm is less than some constant that's about 1/3, which this norm in fact controls the Lipschitz norm and forces your Lipschitz norm to be less than 1. Then under that assumption, then you have a unique global classical solution, and you actually have optimal decay rates for these Fourier norms that match the decay rates for the fractional heat equation. Now, it's also been shown that if you just assume your initial Lipschitz norm is strictly less than 1, you not only have an infinity maximum principle for F, but also for the slope. And they're able to show that from this you can get global weak Lipschitz solutions. Now that same result turns out to be true if instead of initial slope less than 1, you just assume that you're Lipschitz and then monotonic. Now going a different way, Cordoba and Lazar showed that you have global well postness in the intersection of these two scaling critical spaces, where they basically allow you to take an arbitrarily large Lipschitz norm on your initial data, as long as you have the smallness and the H3 halves norm. So there's still a smallness assumption, but it doesn't necessarily have to be smallness of Lipschitz constant. Excuse me. Finally, in this last paper, what we have is the best known continuation criteria. If you have smooth initial data, then everything is fine as long as your slope remains bounded and uniformly continuous. So for there to be blowup, there has to be blowup in C1. Either the norm of your slope blowing up or its continuity breaking down. So my first work, which I did in 2D case, I really combined this continuation criteria and these two results for global weak solutions, then put them all together in order to get this result. It blends between them all. So basically, if the product of your maximal and minimal slope is strictly less than 1, you have a unique global solution. This product of your maximal and minimal slope looks a bit strange at first, but the right way to think about it is kind of an interpolation between these two conditions that we knew gave global weak solutions. If your slope is less than 1, then obviously this product is going to be less than 1. But if you're monotonic, this product is also still less than 1 because one of these two terms has to be 0. And so this condition blends between those results, and it's really an angular condition on your data. The normal of your graph lies in a convex cone of some fixed aperture. You can translate this result to say that. So now, as long as you have that initial assumption, you have a solution that's C1 alpha in time, C11 space. And if you have any additional regularity for your initial data, then it's unique. You basically, for the proof I give in this paper, I just need to really be able to evaluate the equation at time 0. And if you can do that, you should be able to get uniqueness from similar arguments to what I gave in the paper. So that's what's known for 2D. And 3D was known so far is really just analogs of a few of the results that we have in 2D, which makes sense because the 3D case is harder and we still haven't finished on the 2D case. No, so in particular, if you have this Fourier norm that's less than now 1/5, then which still can, this norm still controls the Lipschitz norm, you have a unique global classical solution. What's really interesting about this result is actually been extended to the case where the fluids have different viscosities. And I believe that's the first global, postness results that's been done for different viscosities. Now, if your initial slope is not too large, you also still have a maximum principle for it and global weak solutions. Now, in the paper where this was proven, the result was stated for initial slope less than 1/3. But if you go through the actual argument, it works up to slope 1/√5, which is a bit bigger. And finally, there's analog. Again, analog of another previous 2D result. You take the intersection between the critical L2 space and the Lipschitz space. Then global postness as long as for arbitrary large Lipschitz data, as long as you have corresponding smallness in H2. Now, for all of these proofs and results that are really pushing the limits of what we've been able to do with Muskat, it's my claim that all of the authors are essentially implicitly comparing the Muskat equation to what I'll call the approximate Muskat equation, where instead of a finite difference in this denominator, we have the gradient dot with h, the directional derivative in that direction. So as h goes to 0, these two kernels are really converging to the same thing very quickly. But what's fascinating is that the approximate equation is actually globally well posed. Well, we know that the Muskat equation isn't. Now, let's see. The well-posedness for the approximate equation is really coming from the fact that we have a Lipschitz estimate. And because once, just like with the Muskat equation, once we have a Lipschitz bound, this denominator is going to be uniformly comparable to the denominator for the fractional Laplacian. So it's a uniformly parabolic equation. There's still more work to do, but you can get a lot of regularity out of that, and you can get global postness. Now, this Lipschitz estimate really comes from the fact that this approximate equation has a comparison principle, because it's a general fact that for any equation where you have translation invariance and a comparison principle, you always have a Lipschitz estimate. And so I would call the comparison principle really like the foundation of global well-posedness for this approximate equation. So even though it's a pretty simple argument, I want to take some time to actually go through the proof of it. So I want to see how much of that proof we can still make work for the Muskat equation itself. So suppose we have two solutions to the approximate equation with g less than or equal to f at time 0. Now suppose that at some later time, at some point, g was strictly bigger than f. Up to some technical details, we can reduce everything to the case where we have a first crossing point, t naught x naught. And that is, we have that for any time prior to time t naught, g is less than or equal to f. And then we actually have equality at time t naught at the point x naught. Now, if you take this crossing point assumption and write down all of the things that you can get from it, we get several inequalities. First, the partial differences of g evaluated x naught are always less than the partial differences of f evaluated x naught. The gradients at the points have to be the same. and the time derivative of g has to be greater than the time derivative of f because g is crossing f. Now, that's true for any functions with a crossing point, and now we actually apply our equation. And we have that time derivative of g is equal to this integral, and that's going to be less than or equal to the corresponding integral for f, because the denominators of these two fractions are the same, since f and g at the point x naught have the same gradient, and we have the inequality for the partial differences in the numerators. So that tells us that the time derivative of g is actually less than or equal to the time derivative of f, and in fact, that inequality is strict as long as the two functions aren't identical. So we get a contradiction, and that means that we must have that g is always less than or equal to f, so we have a comparison principle. So my claim is that this comparison principle is the real source for global well postness in the approximate equation. And so my perspective, it's natural to see how much of this argument can we still do with the general Muskat equation. And so to think through that, let's write down the Muskat equation. And if you group terms the right way, it could be written in this form, where it's a function n of the finite difference quotient and directional derivative times some over h squared, which is positive, so it doesn't matter too much. To do the comparison principle argument, fundamentally what you need is for fixed beta, you need the map alpha to n of alpha to be monotonic increase. As long as you have that's true, you can make the comparison principle argument work. And so it's worth actually thinking about, well, what does this function n look like? And it basically just looks like this. The value of beta like shifts things around a little bit, but it really doesn't change anything that we care about too much. For small alpha, the function n is going to be basically just alpha and linear, increasing, monotonic. But then it's bounded, and eventually, for very large alpha, decays like 1 over alpha squared. But what that means is that basically it's monotonic increasing up until it hits some maximum, which we'll say at alpha equal to L naught. And then after that decays. Now, both the finite difference quotient and directional derivatives are controlled by our Lipschitz norm. And so if our Lipschitz norm is less than this L naught, then the value of alpha that we have to consider is only in this stretch where the equation is monotonic, which means the comparison principle argument works. So if you go through and actually calculate like what that value of L naught is, you get that for any two classical solutions for the Muskat problem, with slopes less than 1 over root 5, comparison principle holds. This 1 over root 5 is the same 1 over root 5 that showed up in the paper for the maximum principle for the slope in 3D. Or it's the value that should have showed up in that paper. So I'm not doing better than they did, but up to there. This is really the reason why that holds. And then by the same kind of hand-waving principle, that gives us our Lipschitz estimate, which is the hardest thing to guarantee. And then once we have that, you can get global regularity. So this result is from the 40-page paper where I tried to be very general. And so just to say everything, the most important assumption is this Lipschitz bound on initial data. And then what I realized writing up the paper was that it's not important that the actual interface is bounded, you can allow some like small polynomial growth, really any sublinear growth, so long as you grow slowly enough that this integral is finite. That's the only thing that matters. And as long as you have those assumptions, you have a unique classical solution. That's C1 alpha in time, C1 1 in space. Your directional derivatives obey the maximum principle, and the solution if your growth bounds from time 0, you have them for all time, again, as a result of the comparison principle, which holds. And so for this paper, I do a similar argument to what I did in the 2D case, where we're using the modulus continuity method of Kieslev, Nassau, and Volberg from their proof of global well postness for the critical SQG equation. I'm not going to go too much into this proof because I've given talks about it before, and because the result from my shorter 10-page paper is a bit easier to do using similar techniques. And so I'll just focus on that. Yes, but okay. What this tells us is that as long as our slope isn't too large, we have global well postness. But from an elliptic regularity perspective, there's nothing special about 1/√5. You would really expect that with any Lipschitz bound, as long as your function f is Lipschitz, it solves a uniformly parabolic equation. And so that's the right continuation criteria. The ideal one is just a Lipschitz bound and nothing more. If that stays, if your Lipschitz norm doesn't blow up, you'd expect the solution to be well behaved. And so now that asks the question, well, if we just assume that our solution is Lipschitz, what can we actually say? So assume we have I assume our function f is Lipschitz. Then we necessarily have that the difference quotients are bounded by L. And since trying to generalize the comparison principle, really what I want to do is figure out what assumptions on G can I put in order to guarantee that we still have this inequality at crossing point. Because once that's true, we can push through the comparison principle argument. So we just go back to staring at the same graph and trying to get some inspiration. Like the finite difference quotient, which the variable alpha is taking place of, tells us that for f, the values it takes on this graph can be anywhere up into this point L, because we're L Lipschitz. Now, all we need to guarantee is that when we're testing against G, G is taking values that are always less than the values f is taking. The easiest way to guarantee that is if we reflect this value L back over to here, this corresponding value nu of L. Then if G only takes values in this small interval near the origin, everything is still fine. So if the slope of G is basically about 1/L squared, then we can still make all of our arguments go through. And what we get is this kind of variation on the comparison principle. So if you have a classical solution F, that's L Lipschitz, and you have another solution G, which is nu of L Lipschitz, which is about 1/L squared Lipschitz. If G is less than or equal to F at initial time, then G is less than or equal to F for all later times. And this has, what this really does is open up the possibility of using barrier methods to study solutions to the Muskat equation, as long as we have some Lipschitz assumption. We have to be careful about what barriers we can use because they have to have small slope, but any barriers with small slope we can still apply. this gives us another quick corollaries. The easiest one is that the maximum principle for Muskat, the L-infinity maximum principle, is a natural consequence of this. Because as our test function, we can take g to just be a constant function, which is 0 Lipschitz. And so that's a valid test function for any solution to Muskat. And so that's why all solutions have an L-infinity maximum principle. You can also use this to show that if you have a classical solution and it decays to 0 uniformly at the initial time, then for any positive time, it still decays uniformly to 0. That's not too hard to get. Really, kind of the reason is that we can interpret this imperfect comparison principle in a way that if our solution F is L Lipschitz, then we can control the oscillations of F on length scales that are 1 over nu of L, so length scales of L squared. And because decay to 0 is really at an infinite length scale, the exact value of L doesn't matter, and we can always still prove decay to 0, regardless actually of what L is. So we have good control over oscillations of our function on large length scales. But again, our function F is Lipschitz, and the Muskat equation should be uniformly parabolic. And so we shouldn't just have some bound on the length scale, the oscillations at large length scales. We should have improvement. We should expect things to be regularizing. So that naturally motivates the question, at least to me, can we use this ellipticity to somehow transfer our control over large scale oscillations and shrink it down into progressively smaller oscillations, get regularity? Now, really, for this, I'm very inspired by work of Kislev for the supercritical Burgers equation. Now, for alpha between 0 and 1, consider the alpha Burgers equation, which is usual Burgers, but plus a fractional Laplacian of order 2 alpha, so some diffusion. Now, it's known that if you take alpha to be greater than or equal to 1/2, which is the subcritical and the scaling critical regimes, then smooth initial data has a unique smooth solution for all time. However, if you take any alpha that's strictly less than 1/2, the equation really behaves more like the classical Burgers equations, and shocks can develop in finite time. But now, what Kislev did was in this supercritical regime, he considered the Burgers equation with a little added vanishing viscosity term. So this minus epsilon Laplacian. Because then formally, this equation has a unique smooth solution that exists for all time. And then what he was able to show is that actually these solutions become Holder continuous in finite time, and that time and all the bounds are independent of epsilon. So what that means is that if you take the right notion of weak solution, so if you take epsilon to 0 and look at the right notion of solution, which is going to be your viscosity solution, or I suppose in this case, your entropy solution of the original equation, then those solutions will also be Holder continuous after some finite time. So while shocks can develop, they dissipate. Now, the way that he did this was he showed that the equation propagates a family of Malchus continuity, which are basically a sum of some constant J of t depending on time, then the usual Holder norm, or Holder Malchus continuity. This function J of t represents the allowed size of possible shocks Uh, the initial data was assumed to be bounded between 0 and 1 initially. So at the initial time, we take j of 0 to be 1, and it tells us, this modulus continuity tells us no new information. But we're able to, Kiesler was able to show they can shrink what j of t is over time, shrinking the allowable size of possible shocks until after some finite time, depending only on alpha and beta. You can take j to be identically equal to 0, in which case then this function just has to be Holder continuous. So time 0, we have no new information. Intermediate times, we have control over the size of possible shocks, and then until finally we're forced to be continuous. So that's really cool to me. It's a very interesting idea and argument. And so now I want to do the same kind of thing with Muskat. I was able to. So for ease, let's just assume that our Lipschitz constant L is bigger than 2. Then there exists universal time, T star, which grows at most polynomially with L, such that if we have any classical solution F that's bounded between 0 and 1, and that's L Lipschitz on this time interval 0 to T star, then at the time T star, our function F is actually nu of L Lipschitz. So it's actually 1 over L squared Lipschitz. It's very flat. And because 1 over L squared is going to end up being less than 1 over root 5, and we're very flat, we can then apply the previous theorem and get immediately that in fact this solution has to exist globally for all time. And there's a unique extension for all time. Let's see. So this is almost like, this is, I suppose, adjacent to a Lipschitz continuation criteria. This says that if your solution remains bounded in Lipschitz for a sufficiently long amount of time, then after that time, nothing bad can happen. It has to be regular. All right. So the plan for how to actually prove this is to basically follow the same kind of outline that for the argument Kiesler did with burgers. And what I want to do is show that any solution to the Muskat equation that's L Lipschitz and bounded between 0 and 1 satisfies some modulus of continuity, which I'm going to write down explicitly. Now, in this case, the modulus continuity omega is fairly straightforward. We have one constant j of t, which only depends on time, plus this mess here, which is really just a concave version of nu of L times R. That's all this is. It's a concave version of that function, because concavity is going to be useful later in the argument. Now, we're going to take j of t to be initially at time 0 equal to 1, so no new information. And at time t star, which we're going to determine, it's going to be 0. It's monotonic decrease. Now, for Kiesler and Burgers, this function j of t represent the size of allowable shocks. In our case, we always have the assumption that our function f is Lipschitz, so there's no shocks. But what this number j of t actually represents is really the distance in L infinity from our function f to being a nu of L Lipschitz function. Let's see, so it's measuring how far we are from being a fairly flat function in L infinity. That's the right way to think about it. And we're just shrinking ourselves closer and closer to that ball. Now, the way this argument works, we have to first get a crossing point. So suppose we fix this function omega, and suppose that we have some solution f that So Lipschitz exists on this time interval, bound between 0 and 1. But that this difference, f of x minus f of y, is strictly bigger than omega for some time t in points x of y. Well, by assumption, t has to be positive because every function bounded between 0 and 1 satisfies omega at time 0. So now if you have any kind of reasonable assumptions on f, in the paper I believe I do it for the periodic case, with the period being arbitrary, but you could also do it for a function that's decaying to 0, just anything that'll make this crossing point that force the existence of a crossing point. You assume that, and then we have that there has to be some time t naught that's between 0 and t star in some points, where at the time t naught, our function f has the modulus of continuity omega t naught, and we have equality the points x naught and y naught. Now, then, what this crossing point gives us is really the most useful thing in math, which is a nice picture. And this is what this crossing point translates to. Our function f, which is this black curve, is touched from above at the point x by the function omega. At y is touched from below by minus omega. You can, if you look at this gap below x, you can see that this distance is what j of t is. And now what we want to do is take everything about this picture and extract as much information as we can about the function f. In particular, it's easy to get that the gradient of f at the point x has to be the same as the gradient of omega at this point, which is the same as the gradient of minus omega at this point. So we have that the gradients of f at x and y are the same. As we move away from x, we have very good upper bounds on the finite differences from x, and very good lower bounds on the finite differences as we move away from y. Now, if we put everything that we know together, what we get is this whole list of inequalities, which are, like I said, the finite differences from x naught are always less than the finite differences from y naught. We have a good upper bound on the finite differences from x naught, with the lower bound coming from just our assumption that f is L Lipschitz. We have the reverse equalities for partial differences from y naught. The gradients are the same and equal to the derivative of omega. And if we look at j prime of t naught, which is the time derivative of this modulus omega, because this was a crossing point, that's less than or equal to the difference in time derivatives at x naught and y naught. Now, if you take those first four inequalities and you plug them in, they are actually exactly what you need in order to make the same comparison principle argument that we've been using time and time again work and push that through. It's enough just to have the good upper bound on one of the functions and the good lower bound on another, and that will still work. And what you get is that this difference is going to be up to some constant proportional to the difference in the finite difference of x naught minus the finite difference of y naught over h cubed, the kernel for the fractional Laplacian. So plug this all in. What we have is that the difference in the time derivatives is proportional to the difference in the half Laplacians evaluated at those points. Now luckily, this has been looked at before, in particular in Kislev, Nazarev, and Volberg's paper about the critical surface quasi-geostrophic equation. And they showed that under these crossing point assumptions, you can bound this difference in the difference of the fractional Laplacians. by these two integrals that only depend now on omega, the modulus continuity that we get to choose. We've now replaced an arbitrary function f that's a solution with a function omega with an expression that depends on omega, the function that we actually get to choose. Now, this first integral, both these integrals will be negative because omega we're going to take to be concave. This first integral is really measuring concavity near the point C, near your crossing point, whereas the second integral is really measuring the long-term growth of your function. How sublinear is it? That's what that captures. Now, so now that we have that, we're just going to plug in what our choice for omega was into this expression, and you do a lot of annoying bounds. Nothing is too difficult, but it's just a little tedious. And you basically get that it's always less than or equal to this mess. And now what we're going to do, since we haven't, one thing to know is that this mess only depends upon the value of j at the exact time t naught. And so now we're going to use that we have the freedom to take whatever function j that we want. Now we're going to basically take that right-hand side to be the derivative of j. So we let j be the unique solution to this ODE. And because in the expression for j prime, we end up on the right there with that j to the 1/3 power, pick their j to a power that's strictly less than 1. That's enough to force j to go to 0 in finite time. In particular, if you actually go through everything and calculate, well, how quickly does it become 0? You'll see that it becomes 0 after some time t star that's bounded by L to the 5th log L. So we do use that to actually define what the time t star is. We have our function j, and now we have everything we need to complete the argument. So let f be any's classical solution to the Muskat problem that is L Lipschitz on the time interval 0 to t star and is bounded between 0 and 1. Suppose at some time t we actually had a strict inequality here, and that f did not satisfy the modulus omega. Well, by the same reason before, we can get that there has to be a first crossing point, t naught, x naught, y naught. And if we evaluate at that point, we find that j prime of t naught, which is time derivative of omega, is less than or equal to the difference in time derivatives at x naught, y naught, which we showed is less than this mess, which we used to define what j prime of t naught was. So we get a contradiction. And thus, we have to have that f of t at x minus f of t at y is less than omega t x minus y. So we have this modulus continuity for all time. Since j of t is equal to 0 at the time t star, at the time t star, our function f is nu of L Lipschitz. And then we use that our function f is fairly flat at time t star, so that there's a unique global solution to continue on forward in time. And that's it. So, thank you.